Now, we start with periglacial landforms. Different processes of periglacials result in the formation of various landforms, which can be divided into two main groups: major periglacial landforms and medium and minor periglacial landforms. Begin with major periglacial landforms. Block fields. They are also known as Felsenmeer in German, are created when blocks disintegrate, usually by frost action, that is congelifraction. The high mountain or plateau is surrounded by a continuous spread of broken angular rock fragments of louder dimensions. On steep slopes beyond certain critical angle, the blocks have a tendency to slide down the mountain side. Rock streams. Rock streams are also called rock glaciers or transitional landforms between periglacial landscape and glacial topography. They are accruals of unsorted till-like cores to fine-grained debris with an interstitial ice comprise a glacier shape and distribute down valley. The debris in motion down valley in the shape of a glacier suppose lobate, tongue-like or spatulate forms. The streams consist mostly of matter provided by rock slides, rock falls and ice avalanches, as well as through the processes of glacier, fluvial and wind to some extent. The length of rock streams assumed to be as long as 3 kilometers, and at the toe they attain a height of 60 meters. The rock glacier surface is attributed by linear furrows and intervening ridges, scattered depressions, as well as fresh and permanent snow patches. The rock glaciers' motion is very much like glaciers as they move forward by internal deformation and debris slide of their end, causing in a continuous stream form of transpiration. The basic difference between them is that the rock glaciers are mostly with the debris of rocks with interstitial ice, whereas glaciers are mostly ice which including fragments of rocks. Stone streams. The stone streams, which are the accruals of angular fragments and glacially driven boulders, typically found in valleys and extremely infrequently outside of valley divides. Not all stone streams are periglacial in origin, even though they all originate periglacial areas. Rocks that are sensitive to frost are the source of abundant angular fragments. Fine-grained particles can be washed out from the rock rubble. Stone streams have well-sorted debris, with large debris predominating in the top portion and small debris predominating in the lower portion. This sorting is led by the process of frost heaving. Stone streams go down valley due to solifluction, frost heaving and gravity. Stone streams frequently seem to be a downhill extension of block fields that are located on summits. Asymmetrical valleys. They are the valleys where one side has a steeper slope than the other side. They are structured when slope experiences differential weathering during the periglacial period. This takes place because of different valley alignments result in varying amounts of direct sunlight and shade, and the process function with the varying capabilities on the sunny and shaded slopes. However, there are incomplete agreements over the specific condition of the controls. The direction of the winds is just as significant as insolation. There are numerous ways to produce asymmetry, including one side being steeper than the other, one side being flattened more than the other, or one side being steepened while the other side is flattened. In the northern hemisphere, generally, south facing slopes tend to be steeper than north facing slopes. Greater insulation is anticipated to result in extreme temperature fluctuations, more freeze thawing cycles, and a more active debris mantle, which will cause the steepening of the slope length on south and southwest facing slopes. On the valley side that faces to the sun mostly throughout the day, gelifluction also occur more intense. As a result, the shaded side remains cooler, less prone gelifluction, and other slopes steeper slopes. In addition, rivers are forced to preferentially erode and steepen their north facing valley walls due to the abundant colluvium from the south facing slopes. Cryoplanation terraces. Cryoplanation terraces, altiplanation terraces, or Goledge terraces in Russia are asymmetrical landforms that can be up to 1000 meters long, several hundred meters wide, and 5 or 10 meters elevated at the frontal margins. Since nevation acts around snowbanks and settles them in pre-existing alloys, and on steeps, many of the terraces are cut into solid rock. The debris created by nevation may be removed with the use of solifluction. Now, medium and minor periglacial landforms. Begin with ice wedges. The ice wedges are ice-filled cracks or fissures in the ground that often extend below the permafrost mantle. These are V-shaped, typically vertical, and appear milky white because of numerous tiny or bubbles inside. Every year, thermally induced permafrost cracking gives rise to formation of ice wedges. The top permafrost horizon contracts as a result of the extreme winter cold below -15 degrees Celsius, forming minute fissures, while water from the active layer percolates down to freeze beneath the permafrost table in spring, creating ice veins. Hoarfrost accumulates in the cracks or fissures during the winter. The sediments deform and upturn against the ice veins as a result of thermal expansion brought on the rising temperature of permafrost. The cracks are reopened in the next winter due to renewal thermal contraction, and the entire process is reiterated. The cracks reopen, filled, and freeze once a year, forming an ice wedge. Horizontal surfaces made of fine alluvial sediments are ideal for the development of ice wedges networks. Therefore, they stand out especially on floodplains and river terraces. Ice wedges may be syngenetic or epigenetic in nature. Syngenetic types emerge in the tandem with sedimentation and extend upward as the ground surface level rises, whereas epigenetic types appear after the termination of fluvial aggradations. They can develop about 2 feet, that is 60 centimeters or more in width, and 3 to 15 feet or more in depth. Sand wedges. All the wedges do not form like the ice wedges formed. Fossil wedges like structures may result from the decay of massive tree roots, and sand wedges are one such type of landforms. Sand wedges suggest a relatively dry and windy environment in contrast to ice wedges, which symbolize the humid polar climates. These wedges arise as a result of wind-blown sand continuously filling in the frost cracks. Sand is added to the expanding construction every year until it may potentially reach a width of more than 1 meter. These are prevalent in Antarctica. Involutions. Permafrost regions represents to deformation of layered sediments of unconsolidated materials located immediately below the ground surface in permafrost areas. Deformation seldom is so prominent that original formation develop into indefinite and undetectable. These formations have been observed in alternating beds of silt, clay and sand with the variable grain sizes. The development of involution is resulted by several factors, and the diverse enlightenments for their formation include intergranular pressure changes during thawing, expulsion of pore water to unfrozen sediments during freezing, different volume changes due to freezing of pore water. If the adjacent material remains unfrozen, it is squeezed and eventually engulfed by the expanding frost heaved material. Summary. The periglacial landscape is attributed by extreme frost action and existence of permafrost, which results unique processes such as jelly turbation, jellyfraction, solifluction and nivation, etc. The periglacial environment is dynamic in nature and it is structured by various factors such as geology, climate, terrain, vegetation cover and so on. The periglacial landscape is characterized by several small scale and large scale landforms, which include striations, block fields, ice wedges and sand wedges, etc. The periglacial landscape is sensitive to climatic changes and dynamics of precipitation and temperature, which significantly transform their forms and processes.